T naught is the dead time, which is also measured in seconds. And then I'm going to show you in the next few slides how we were able to get all those values. This is one of our trial runs with an input power of 70 to 80%, with our frequency at 0.4 hertz. What we'll do is we'll take a bunch of trial runs at different frequencies, and we're able to create a Bode plot after we get our phase amplitude and our our amplitude ratio and our phase amplitude. Phase angle. Sorry. Here you can see how we got tau, our period. It's just the difference in the time at the peaks of our input power, which for at 0.4 hertz on the higher input power was 2.5 seconds. Our change in M is just our change in input power, which is double the amplitude, which we got to be 10%, which is here. It's just the difference between the peaks of the input power. T we use to get the amplitude ratio, or the phase angle, is 0.15 seconds. It's just the difference between the peak of the input power and the output voltage. And change in C is the difference between the peak of the output voltage and the bottom of the sine wave. So what we did also, we got all these values for every one of these frequencies for each input power range. We did it 3 times at each of the last 3 peaks, or at least each of the last 3 periods from peak to peak. Here's our graph of our output voltage versus our input power. It shows our change in M, our change in C. And then this is a Bode plot with all of our, this has all of ours on it. Here you have, I showed you how to get on here the ultimate gain, the order, and it's got the ultimate frequency on here. I'll show you how I got that on the next slide, but you need it to get the ultimate gain. The gain is just what, it's what the amplitude ratio approaches as the frequency approaches 0. Our order is the last leg here, where it starts to, where it's after the corner. It's just the slope, which I drew a line parallel from one, like, I guess you'd call it a unit square of the log plot. And then to get the ultimate frequency, what we did, well, we did on the next slide, but when we got the ultimate frequency, we just drew a line up to where it meets the amplitude ratio, and drew it across to get the critical, well, to get the amplitude ratio there, and then the reciprocal of that was equal to our ultimate gain, which was, for this it was 2% per volt. Here's the bottom half of the Bode plot. We were able to get the ultimate frequency here by just finding, so it kind of moved. But we took the line from negative 180 degrees here and drew it across, and it would hit right there, which is at 7 hertz, and then we were able to use that to get the ultimate gain. Here I was talking about how it doesn't do that.
I didn't do it.
So also, you can, if you notice, it seems that the farther along you go, the higher the frequency gets, the higher our uncertainties get at all these values. That'll come in handy later. Well, it might come in handy, but I'll show you why we support it. We're able to solve for the first order time constant tau using the formula for amplitude ratio, which is the gain over the square root of 1 plus 2 pi f squared tau squared. And also our dead time T naught can be solved for using our equation for phase angle, which is negative 2 pi f T naught plus the inverse tan of negative 2 pi f tau. Those formulas are also used for modeling our Bode plots. That's how we got our amplitude ratio phase angles for those. And here's our models for our input power of 0 to 69% here. You can see that it's pretty similar. It dips a little here and it's a little over there. This is just the top half with the amplitude ratio. Here's the bottom half of the same one for the input power 0 to 69%. You can see here there's a huge difference. The uncertainties just start getting larger and larger the further you go along with the frequency. One thing that was important was we wanted our data to match as closely as possible in the beginning, because those generally have smaller uncertainties. And for 69 to 70%, this is our amplitude ratio versus frequency. Here, it stays pretty close in the beginning, and then it just never dropped here. We're not really sure why that happened. This is the bottom half, the phase angle versus the frequency. And it doesn't match great. It's as close as we can get it. But you can see that uncertainties are very large, so that's probably why it doesn't match too well. And here's the amplitude ratio versus frequency, the top half of our voting plot for an input range of 70 to 80%. You can see it matched very closely at the beginning, and then it's off a little here and there, but it matches fairly closely to the model matches very closely to the experimental. Of course, for all these, the ones with the line are the model, and the other points are the actual. And the bottom half here, again, we're really close to the beginning. You can see the triangles without the line, or the actual, and the line with the squares or in blue, or the model. It matches really closely in the beginning, but then as the uncertainties start getting larger, it kind of gets off a little bit. Another thing that was really important is we wanted our models to our model to match the experimental at the ultimate frequency, where the phase angle was negative 180 degrees. Here's after we got all those values for each of our input ranges, and our gains were from at the lower input range of 0.15 volts per percent, in the middle it was 0.7 volts per percent, and at the higher end it was 1.8 volts per percent. Our T0 was 0.6 seconds on the lower range, 0.04 seconds in the middle range, and 0.15 seconds at the higher range. Our tau was 0.93 seconds in the lower range, 0.40 seconds in the middle range, and 0.04 seconds in the higher range. Our order was 1.0 in the lower range, 0.4 in the middle range, and 0.8 in the higher range. And then our ultimate frequency was 4.5 hertz, 6 hertz, and 7.6 hertz, respectively, for each range. And our ultimate gain was 0.2 percents per volt, 1.4 percents per volt, and 4% per volt for each range. It varies quite a bit. If you saw from Rachel's presentation, our steady state operating curve, it was not linear at all. It kind of was all over the place. So kind of explains why we have such dramatically different data for each range. And then I've got it in a table like this so that somebody, if they needed just to be able to glance at it, they could get all this information in one place. I also wanted to compare our step-up responses to our sine responses. You can see that our data changes quite a bit sometimes, and sometimes, like here in 0 to 69% input power, our gain is very similar. The step response is in blue and the sine response is in red. For 69 to 70%, the step response is a lot higher than the sine response, and the same is true for 70 to 80% input. Our dead times are kind of all over the place relative to each other between the step-up response and the sine response. From 0 to 69%, the sine response is quite a bit bigger. From 69 to 70%, the step-up response was much, much larger than the sine response. As you can see, our sine response was about 0.1, and our step response was about 2.1 seconds. And then it was much smaller. The sine response value for the dead time was much smaller than the step-up response as well. At the high input power range. Our time factors were all much smaller for the sine response value relative to the step-up response. You can see each one of these, the low, middle, and high input power ranges, there's a huge difference. It drops a lot. Does anybody have any questions? Thank you for your time.